A sequence is formally defined as a function that has as its domain the set of positive integers, for example, 1, 2, 3, up to some number. Exercise 1. A sequence is defined by the equation a of n equals 2n minus 1. Find the first three terms of this sequence denoted by a sub 1, a sub 2, and a sub 3. Now, your notation, this is function notation, and this is subscript notation. They are interchangeable. So I could be finding a of 1, which is the same as a sub 1. So you have to get used to the different kinds of notations, function notation or subscript notation. So the first three terms, well, the first term, notice, a of 1, n is 1. So 2 times 1 minus 1 is 2. A of 2, or a sub 2, is 2 times 2 minus 1. And notice again, 1 and 2 are my n values. So this one is 3. And a of 3 is a sub 3, and that's 2 times 3 minus 1, which is 5. Did you notice I already made a mistake in the first one? This should be a 1. Great way to start. Now in part B it asks us which term has a value of 53. Notice the value of the term is right here. That would be our answer. The term number is the subscript or the function notation in parentheses. So if I'm looking for which term has a value of 53, I'm looking for the function notation or the subscript. So 53 is my answer, and that equals 2n minus 1. So add 1. So 54 equals 2n, divide by 2. So n equals 27. So the 27th term, so a of 27, that's not a 7, a of 27 is 53. So the input is 27, the output is 53. Right back to our function notation. So explain why there will not be a term that has a value of 70. Well, notice our four values, 1, 3, 5, 53. If I multiply by 2, it's going to become even. But as soon as I subtract 1, all my terms are odd. So, recall that sequences can also be described by using recursive definitions. When a sequence is defined recursively, terms are found by operations on previous terms. That is huge. So in order to use a recursive definition, you have to know the previous term. So in exercise 2, a sequence is defined by the recursive formula f of n equals f of n minus 1 plus 5, with f of 1 equaling negative 2. So if I'm looking for the second term, it equals f of the second term minus 1, which is f of the first term, plus 5. So really, when I look at this, the formula is just saying to find the next term, it equals the previous term plus 5. So this is telling me that the first term is negative 2. So I just have to find the second term by adding 5, third term by adding 5, the millionth term by finding the 999,999th term and adding 5. So generate the first 5 terms of the sequence, label each term with the proper function notation. So f of 1 equals negative 2. They gave that to us. So now f of 2 equals f of 2 minus 1 plus 5. Well, 2 minus 1 is just 1. So this is the same as f of 1. And I have to add 5. So f of 1 was negative 2. So negative 2 plus 5 is 3. So again, what did I do to negative 2 to get 5? Or to get 3? I added 5. So I wanted to show you in this first one how we got it, but really we can just keep adding 5. So f of 3, add 5, we get 8. f of 4, add 5, we get 13. f of 5, add 5, we get 18. So all it's saying is add 5 to the previous term. So in part B, determine the value of f of 20. Hint, think about how many times you have added 5 to negative 2. So think about this. In the first term, how many 5s did we add? None of them, because they gave that to us. In the second term, we added 1 5. In the third term, we had to add 2 5s. So 5 plus 5 plus negative 2 is 8. In the fourth term, we had to add 3. So if I kept going, the fifth term would be 4, the sixth term would be 5. So I'm adding 1 less 5 to the term I want. So if I want f of 20, I have to take a negative 2 and add to it 1 less 5, so 19 5s to it. So your answer is 93. So it's really important you understand in this question, when we talk about finding terms way far down the road, we want to add or subtract, because we could be going down, 1 less the number of terms, that many of our adding or subtracting item from the beginning. And that's going to come into play in a few examples. So determine a recursive definition in terms of f of n for the sequence shown below. Be sure to include a starting value. So we have 5, 10, 20, 40, 80, 160. So 5 is our first term. 10 is our second, third, fourth, fifth, sixth. So f of 1, our first term, is 5. We have to know where to start in a recursive. What is our pattern doing? So what are we doing to 5 to make 10? What are we doing 10 to make 20? What are we doing to 20 to make 40? And so on. Hopefully you said multiplying by 2. So think about your recursive up here. F of n equals f of n minus 1 times 2. So if I need the second term, it equals the first term times 2. If I need the fourth term, it equals the third term times 2. If I need the 100th term, it equals the 99th term times 2. Not a very efficient formula. So go ahead and pause the video and try example 4. Hopefully you got the answer of choice 4. You can see my work here. So the first term they gave us, the second term equals the first term squared plus 2. Well, the first term is 2, so 2 squared plus 2 is 6. The third term equals the second term squared plus 2. Well, the second term is 6, so 6 squared plus 2 is 38. The fourth term is the third term squared, so the third term is 38 plus 2, which is 1446. To me, this recursive stuff kind of reminds me of compositions. You take your answer and plug it in, get a new answer. Take that answer, plug it in, get a new answer. Take that answer, plug it in, get a new one. I hope that makes sense. Exercise 5. One of the most well-known sequences is Fibonacci, which is defined recursively using 2 previous terms. Its definition is given below. F of n equals f of n minus 1 plus f of n minus 2. So what that means is, say the fifth term equals the fourth term plus the third term. So they gave us the first and the second term. So that means the third term, f of 3, equals f of 2 plus f of 1. So this means the term below it and two terms below it, or two previous terms, the first previous term. So our answer to f of 3 is 1 plus 1, which is 2. So now f of 4 equals the previous term, which is f of 3, plus the second previous term, which is f of 2. F of 3 we just found, which is 2. F of 2 is 1, so 3. F of 5 is the previous term, f of 4, and the one before that, which is f of 3. So f of 4 we just found is 3, plus f of 3, which is 2, so 5. And the last one, f of 6, equals the previous term, f of 5, plus the one before that, f of 4. So we just found f of 5 to be 5, and we found f of 4 to be 3. So f of 6 equals 8. That's a tricky one, so you have to know how to read the recursive formulas. Exercise 6. Find an algebraic formula, a of n, similar to that in exercise 1 for each of the following sequences. Recall that the domain that you map from will be the set 1, 2, 3, ... all the way up to n. So why don't you pause the video and see if you can figure out some formulas to go from the first term to the second term. And you're using 1, 2, 3, 4, 5, 6, and so on as your n values. Good luck! All right, let's see how you did. For letter A, you should have a of n equals -1 to the n power. For letter B, you should have 2 to the n power. For letter C, you should have a of n equals 5 over n. And letter D, you should have a of n equals 1 over n squared. If you couldn't figure those out, then make sure that you ask in class. Go ahead and pause the video again and try number 7. All right, so I found the first three terms, 3, 5, and 7. I made an XY table, and I know the answer is choice 3. Why is it choice 3 and not choice 4? Well, again, your n values, if you go back to the beginning of this whole lesson, is from the set of positive integers. So I can't have in between 1 and 2 because there's no integers between 1 and 2. So they are specific dots. I don't have 0 because 0 is not a positive integer. So it is choice 3 because n is from the set of positive integers. All right. Good luck with this. Any questions? Ask in class.